Okay, the record is on. So, after the beams, we shall move on into the frames. And if you can see from the previous examples that I can break the beams into many portions, the one before that, we needed 3 portions, 2 for the cantilever and the 1 for the midspan. And the one before that, it's a cantilever beam with 2 different EIs. And so we need to break that into 2 portions as well. So things are pretty similar with the frame. The frame for this, the one that we mentioned very earlier last week, you can see we have 3 members. So it's pretty much the same fashion. We need to write a moment equation for each portion, and that's it. Okay. So we may have mentioned this about the virtual work, but let's see, before we go into the virtual work, say I can also try to show you how to calculate the horizontal displacement at D now. Okay, so not only that you have to be able to analyze the frame, but you must also be able to draw the moment, to write the moment equation. Okay, in doing so, we are going to break down this frame into multiple portions again. Okay, so this is our frame. Yeah, that's that. And we have 800 applied here. So the moment in this, it's like 32. So it's going counterclockwise in this fashion. So I need the clockwise couple from the reaction. And this is going to be 800 multiplied by 4. Oops, sorry. Because 4 is the distance in this direction, right? That's a moment from 800, then divide by 6, which is this is 6, the distance of the moment arm of the couple. And then again, this is 800 multiplied by 4/6. So now we need to break this into, oh, okay. And we also need to have 800 here. So now when I look at the first piece, let's give it some name. A, B, C, D. Instead of drawing the free body diagram and bending moment diagram, now you need to write the moment equation. So when you look at AB, okay, basically that's your free body diagram, correct? And that I'm too tired to write this number, so and it doesn't produce any moment. So I am going to just use this piece, and now if I begin from here, my moment equation, let's write them here right away. It's going to be, let's say I view this as a negative moment because I prefer to look at the frame from inside, and that's my direction. So my moment becomes 8 minus 800x. Okay. And now we move on to, let's say before that, if this is 800 and that is 4 meters, now you know that this is going to be 3200 kilogram meter, right? Yeah, that's a complete free body diagram. So move on to member. Okay, I should write that this is AB. Move on to member BC now. My BC, it is going to have this moment coming with me, 3200 kilogram meter. And now this reaction is going to come. It is 3200 over 6. Okay, and that means this has to be another downward reaction. So now you have a choice. If you write from left to right, as usual, your moment equation is going to be minus 3200 plus 3200 over 6 multiplied by x, right? But if you choose to, let's say, B to C, but if you perhaps choose more smartly and you begin your x from here, your moment equation can be again, because I position myself here inside the frame, I'll see this as a negative moment of 3200 over 6x. Okay, so you got your two choices, but if you could complete your free body diagram, this is super piece of cake. Okay, and for CD, apparently it's a zero force, zero moment. Okay, so I don't need to do anything about it. Now, because I want to have the horizontal displacement at D, I would take this frame and apply the unit force here at D, because I want to know displacement at D, and in the horizontal reaction, because I want to know horizontal displacement. Yeah, I said horizontal reaction, horizontal displacement. Okay, so and then we proceed to analyze the structure as usual. Okay, so this is virtual. And now reaction wise, because this is there, so your reaction is going to be this. See, that becomes your reaction. And now we proceed to do as usual, but don't forget to be consistent. Okay, so let me go into member AB. What's going on? That's my AB. That's one. So that means I have another one there, and because they do not coincide, I have the moment of one multiplied by the length. So that's 4 kilogram meter. Okay, and my moment equation will be small m equal to minus x. Move on to this piece, BC. This is also 4. And because I don't have any vertical reaction this time, so that's just going to be 4. Right? And this is one of the most dire mistake that many students can make, that they always forget that this piece has moment. They generally, okay, it's 0 because I have a force here. But if you look at the free body diagram, you would know that this is always there, and therefore this piece has moment, but it's a constant. So it becomes pretty easy that our moment equation here is all right, minus 4. Okay, so in the end, it doesn't matter whether or not when you look at the actual load case, you want to write the moment equation from maybe I should use this, from left to right or from right to left. If you don't believe it's going to give you the same answer, you should try. Okay, so now we've got everything. It's just time to sum up all the work done by all the members in the system. So it's pretty straightforward. use black will be fine. So I can easily say now that how do I call it? Called delta, right? Delta D in the horizontal direction would be the virtual work of the first member. Now, maybe, before I do that, let's, oops, I only have that much area. So give me, I don't have the space to write the summation. So the first integral will be from 0 to 4. This is for member AB. The actual moment is, which one? Yeah, minus 800x. Okay. Oops, sorry. Minus 800x. And the second is the virtual moment of minus x dx over EI. And then the work of the second piece is from 0 to 6. And since they should be the same, so I'm just going to use the easier one. Minus 3200 over 6x multiplied by minus 4 dx over EI. And play some calculation music. This is gonna come out to be equal to 55467 over EI. Okay. And it is coming out to be a positive because this frame is being pushed by the 800 to the left. And I apply this imaginary unit load to the left. So naturally comes out to be the positive. So you see, it's only gathering up the work of the entire system. And in this case, our system has 3 members. So it's not really different from the last beam that we did in the previous session. Okay, so now let's move on to another frame that I prepare for you. It's going to be a long way down here. Is there any option that allow me to move down quickly? Okay. Here they are. Oh, wow. Now, again, this structure, it has 2 members, but because of the presence of the point load in each member, you cannot have one integral because your moment diagram is not going to be like one straight line or one straight or one curve. Okay. So yeah, hard work again, isn't it? So we would try to think about the smartest choice that we can do in terms of, the best or the easiest way to carry out our integration, right? That's kind of fun. I kind of like it. What should I do? Spend time thinking, planning to try to work as little as possible. Okay. So before anything else, let's complete our reaction here. Okay. That's going to be 1 up. Going to be 1. And the moment here, you need to include the effect of the 2 loads. And in the end, say this is 4 ton meter. Okay. So let's give it some name as well. Okay, so this is A, this is B, C, D, and E. Okay, and you can see that this load, see, it's not perpendicular to your member. Be careful. We need the one perpendicular to the member. Okay. And what do we need to do here? It says that we need to calculate vertical and horizontal displacement and rotation at A. So wow, it's like 3 more things. So this is the examples, just fine, right? So let's say we have this. Oh, too short. Okay. Let's say, I think if I use different color, it'd be better, right? So that you can differentiate each load case. So let's say vertical, okay, pink. To obtain the vertical displacement, I need to apply the vertical load, unit 1 here. So let's say this is for vertical displacement. Okay, that's 1. This is 1. Because they are 7 meters apart, that's 7. Okay. Second, horizontal displacement. So again, it's the same thing. But this time we apply the horizontal force instead. This is for horizontal displacement. Okay, if that's 1, this is 1, and because the force don't coincide, so there's moment as well. That's 4 because they are 4 meters apart. See, and then the last one. We want to know rotation, so we apply unit moment for rotation. This one is pretty easy because there's no other force. So if you have moment there, you also have moment there. You might want to say, okay, this is what you apply. Okay, just put the quotation mark on it. Okay. All right. Oops. Say this is also 1. Now it's just nothing else. We just need to, write the equation for our structure. Okay. And you should see that for member AC, the first portion under the actual load AB, there's no load, so there's no moment. In fact, we don't need to do anything about it at all because everything else will be 0, right? Because there's nothing on the actual case. So our case would begin from here, B. And you need to turn this load onto the one perpendicular to the member. So if that's the angle, this is the angle. So it's the sine theta of that. Okay, so I can just write the moment equation. Portion. Let's skip AB, all right? So it's BC. Big M. That load perpendicular is going to be, because this is a 3, 4, 5 triangle. So sine of that, sine is 4/5. So this is 4/5. Okay, so my moment will become minus 4/5 multiplied by, because I don't know if it's necessary, but that the way I did it, I wanted to start from this for every one because I have the load at the tip, so it's probably slightly easier for me. So I begin, my x is here. So this becomes x minus 2.5. Why 2.5? Because the length of member AB, if you look at the projection, the length here is 5 meters and the point load is in the middle here. So I begin everything from the point load. That's where my x is equal to 2.5, right? So that's 2.5 meters. Okay, maybe not the smartest choice, but you know, it would be crazier if we try to redo it now. And that's for my BC. What do you want me to do? You want me to complete the BC for every portion, or you want me to complete the actual case first? Thanks a lot. It's quiet as usual. So I'm just going to complete this. The next portion is for DE. But I would rather write my moment from E inward, because I don't want to calculate moment at C, right? It's not necessary. So I begin with the reaction here. So that would be -4 constant moment in the negative way. And then I have the upward reaction equal to 1 here, as you can see. Okay, so plus X. And then I move on to the portion the CD. Portion CD. You can see, in fact, that because this reaction here is accounted for this one. So when we are beyond point D, the shear force comes down to 0 and the moment becomes constant. If you don't believe me, you can try to draw the free body diagram of member CD, right? And before that, you probably need ED. That's for E. I think my iPad is running low on RAM. That's why it does that a lot. If that is 1, you need 1 downward. And then you have a moment here of 4. This one produces 2 up, so you have 2 more here. Okay, so that's why for CD, you just have only a constant moment equal to -2. It's negative for me. Too quick? Well, the frame is something that you should have mastered before the midterm exam. Okay, so let's see if we have a spare time, I can come back and elaborate on this. But you know, for free body diagram, DE and CD, you should just be able to, you know, chuck it away just like that. Okay. So now that's done. Now is, I should write the range somewhere. Okay. And let's say you guys know it. All right. So let's move next to this case. The case for vertical displacement. So it's going to be the pink one. Oops. It's going to be the pink one. And again, I'll start from BC, but then because I started like this, so the range is, in fact, it's right somewhere. Range is 2.5 to 5 for the range. Okay, so the pink moment, oops, beginning from that. Again, this is a vertical one, so here is going to be 4/5 as well. Oh no, this is a horizontal one, so this is going to be 3/5 instead. My apologies. But then if you begin from 2.5, so it's pretty simple for me. This is going to be just -3/5 multiplied by x. Okay, and we have this from E to D. So I need to include the reaction here. So it's going to be -7 plus x, right? Because we begin from here as well, to avoid calculating the moment at the joint. And for this portion. Now, because we only have that, there is no interruption from any external load here. So this one maintains minus 7 plus x. Okay, and let's put a barrier here. Let's move on to the next load case. That is the horizontal displacement. Oh, I did that a lot. Horizontal displacement. And now this case, yeah, it's a horizontal load, the same. So it's going to be minus 4/5 of x. Okay, because I use a range like this, so I don't have to do anything with these two terms at all. It's pretty straightforward. And for dE, we begin from here. So it becomes minus 4. And then that's it, because we don't have the vertical load in this case. And this is also minus 4. Yep. And the last one for rotation, the moment is gonna be minus 1, and minus 1. Like that, huh? Okay. I think we can move this back in. Okay. And the range, yeah, let's finish the range. dE, this is from 0 to 2. And then, in fact, you could use the 0 to 2 or 2. Oh no, we have this equation, so it better be 2 to 4. Okay, so then that's it. After you use your proper engineering knowledge to write the moment equation, it's just about the assembling the proper equation for virtual work now. So for delta, A, the delta V at A, okay? It's gonna be these two, right? Oh. All right, so first one, 2.5 to 5. Oh, in fact, we have also the different moment of inertia. So let's erase B out of the way. That's I and that's 2I, so pay attention, okay? So here, it's the first pair, oops. So this is minus 4/5 x minus 2.5. That's the actual case, multiply with 3/5 multiplied by x, okay? And then it's dx over EI. And then we have two more terms, okay? Plus integral from 0 to 2 minus 4 plus x, and then minus 7 plus x dx over 2EI plus the last integral from 2 to 4 minus 2 and then minus 7 plus x. Again, dx over 2E. Oh, that's it a lot. Oops, what did I do? Okay, wrong one. 2EI. Okay, so that's the first one. Okay, and this gives us the number equal to 32.58 over EI. It's a positive value, which means positive means actually it means that the direction is similar to the direction of your unit load, right? But I would just, you know, summarize it. That means it's a downward deflection. Okay, and well, you know, it's more of the same. I'm afraid that you are tired, you know, so but maybe it's for the good reference. So I'm just gonna soldier on and try to finish this. Okay, so the second one, the horizontal deflection at A, it's gonna be integral. First one again, 2.5 to 5, and now we have the same function. Let's do that. Minus 4/5 x minus 2.5. This time it is going to be this guy right here. So it's 4/5 of x, the negative value. Excuse me. Okay, then this is dx over EI plus integral from 0 to 2. The function is the same. Okay, minus 4 plus x. This time multiply by 4/5 of an x as well. Is that right? No, it's a constant moment. Let me check. Yeah, it's constant moment of minus 4 now. But you see, okay, that's right. Nothing. Okay, this is minus 4. And then the last one, from 2 to 4, and we now have the same, right? Constant moment, and then this is also a constant moment. Dx over 2EI. Got this. Dx over 2EI. So that gives us the number 28.33 over EI. Again, it's positive, which actually means the displacement goes in the same direction as the applied unit load. Okay, so that is this. Okay, guys, the last one now. Zeta A. This is going to be, again, this one. I got something this negative here, okay? And then this will be multiplied by what we got for rotation, which is always minus 1. Should be easy now. Minus 1, and then dx over EI. And then in fact, it means I could actually copy everything here. pace. And then I would fix this. See, so the main function is there. We just need to replace the small m with -1 here, and then -1. So actually copy and paste will let you see that, well, what is a repetitive part of the integral is the actual moment part remains the same. You just need to match them with the virtual part. Okay. And this gives us 7.5 over EI, and it's positive. So that means positive. Oh my, look at this. This is not about my handwriting. It's just because it seems like iPad is running very low on memory. Okay. Positive means it's going the same way as our apply unit moment. Okay, so that's it. Wow. Am I going too quickly? There's no one talking to me about anything at all. So I'm just keep steady, maybe a little bit too quick. So is there any question? Well, let me stop the record first.